Hey guys, so here is a more example regarding to apply the Lenz's law. And let's see what starts with the figure A, figure P. And in this case, when we have the two rods, they are go away from each other. So in that case, the loop will be increased. The loop increase will be lead to the flux will be increased as well. So since the flux increase, what happened for the induced magnetic field? According for the Lenz's law, it's called induced here. When the increased magnetic field, the loop will be try to resist this acting by try to get the magnetic field or down. So generate the induced magnetic field to resist that action. So it means generate the induced magnetic field, and that magnetic field or the induced magnetic field will be point out to reduce the increase. So here is the pointed out. So magnetic field will be point out of the page. Using right hand, so we have the magnetic field pointed out, so we can find the direction of the induced current will be in that direction here. So what we have the induced current. Induced current will be counterclockwise. Counterclockwise. Okay. So let's move for the figure C. Figure C, we have the magnetic field point to the left side in the same way or the same direction of the rod directions moving out. And in this case, the magnetic field with the conductor, they are in parallel. There is no angle between those things. So here's what we end up. There is no flux. No flux in that case. There is no flux. That means no change in the flux. So the flux is zero. So it means there is no induced current. The same thing is no induced current. Because even the induced magnetic field will be zero. So the induced current, there is no, we call it induced here to be clear. It will be no induced magnetic field. We saw the situations here when we use the emotional EMF. Let's see more example for the Lenz's law, just to see multiple choice or multiple situations that we can figure it out. We can find the direction of the induced current. Let's see this example here. We saw those two examples before in the emotional EMF. Now you can get back and compare your result with this one, and based on the situation that you have or what the way that you're comfortable with, you can use the Lenz's law or use the emotional EMF. And here we are focusing about using the Lenz's law instead. So here in the D, figure D, we have triangle here, and they are pointed to each other. So what that means? That means the area will be decreased. So that means here's the flux will be decreased as well. The flux will be decreased or decreased. Okay. So the flux will be decreasing. What that means? According for the Lenz's law. According for the Lenz's law, when the flux decreasing, they're gonna be resist that actions. Resist that actions, gonna decreasing, try to increase that one. So B induced here will be try to increase it or the replace that decrease. But decrease that one will be point out of the page. So what that means? You're gonna generate the magnetic field pointed out of the page just to replace that directions. And according for that, to find the induced current directions, it will be using the right hand will be that directions. Again, for that direction here, from the respective counterclockwise, this one's the induced current. We're gonna be counterclockwise. counterclockwise. So let's see the last example here in the F. When we have the rod is move up, but is away or the out of magnetic field area. So no matter what the loop size is, since it is out of the magnetic field, it's gonna be the flux will be constant. Here's the flux. Flux will be constant. Since the flux is constant, there's gonna be no induced magnetic field. There's no induced magnetic field. And there is no induced current. Induced current. So for more example, and in that case, when the right hand or hard to apply the hand or right hand rules, which that's similar to what we did in the lab last week. So we have here is a magnetic field. Oh, sorry, magnetic rod, and the North Pole goes down, and the loop right now is constant. There is no change with the loop. So now the only change here, the magnetic field when it's be pointed or the push it down to the loop, and what's happened for those situations. So let's draw the magnetic field lines based that go out from the North Pole. So will be pointed out in that directions. In that directions here outside of the north. And that direction of magnetic field. When we push it down here, have the same thing, but the only change we have, the magnetic field, when we are close to the loop, the magnetic field will be increased. So here is the P increase. So based on the Lenz's law, change the color. When we have the flux increase, so here's the flux increase as well. So when the flux increase, the induced or the loop will be generate induced magnetic field, try to resist that one. So which means I have the magnetic field or the induced magnetic field in the right word. Induced magnetic field will be resist that increase by generating the magnetic field point opposite direction. So here is the magnetic field opposite direction. So here here the flux in that case gonna be increased, and induced magnetic field will be point up, and induced current is in the right hand, it will be goes that way. So what that way here is the directions counterclockwise directions. Let's apply more example. Let's see that case. We have the same situations here, and now only thing is different. The starting point here, the magnetic field was very close to the loop, and then move it away from the loop. So again, we're going to draw the magnetic field. Gonna be that directions. Now change with that. Here is the magnetic field. Now when I push it out, so the change here, the magnetic field lines will be away. So that means the magnetic field will be decreased. So here's the direction for that case. Which basically what I have a flux decrease. So here is the flux will be decreased according for the Lenz's law. The loop tries to resist that one by increasing the magnetic or the induced flux or magnetic flux be induced. By increasing, by generate more magnetic field, we go to the same directions that the original magnetic field goes. So we're going to be generate a magnetic field, gonna be go that way and go to that way. So here will be point N, point down. If you want to say the direction of the induced magnetic field will be down. So based on the down, so the magnetic field will be this direction using the right hand rule. You can double check for the direction the current. So here it will be clockwise directions. Last example here for that case, what the direction of the induced current, the loop viewed in that situations before. What do we have on this figure here? We have the magnetic field. We're gonna be close to that case. So again, magnetic field lines will be point out from the north side, north pole. Here's the magnetic field. And when we push it close to the loop, that case will be what happened for the flux. Flux will be increased. Flux increase. So flux increase, Lenz's law stated we have to, or the loop should be generate the magnetic field to resist that increase. So we need to opposite or to cancel that increase. So we generate the magnetic field point down. So here is the induced magnetic field, this one. We call it P induced. Where is it going to be pointed? Is it going to be pointed down? Right hand rules. We will find the direction of the current will be pointed in this directions here, counterclockwise. So here is the current is clockwise, counterclockwise. The answer will be B. Just more practice for the Lenz's law.